Okay, great. Cool. Yeah, thanks again for making time for explaining me your
Yeah,
work.
I heard you have some more questions from last time, and
Yeah,
the last question you asked, I was not able to answer it because the 40 minutes were over. Yeah.
yeah, exactly. Exactly. So yeah, I emailed you with a number of questions, but the okay, I did buy your book, so I will definitely read it. So I'm really looking forward to
Yeah, thank you.
learning from your work. But before I dive into this mega book, just
Mhm.
I don't know how many pages,
Yeah, and
I
there's
really
actually some new content now. Yesterday, I figured out something about exotic matter. Uh,
oh okay, oh right, okay. So that will be on the next book
well,
iteration.
that's
So
problematic because it already reached the maximum number of pages. So I'll have to split up the book into, it's pretty thick already, so
ah
cannot make it any thicker. Mm,
oh right, I see. Yeah, okay, makes sense. Yeah.
mm,
Um, okay, so I'll go from the humble steps that I'm not yet there.
yeah.
So my my questions were regarding first of all, in your framework, how do you explain inertia? That was not clear to me on the
Yeah.
previous
So
discussion.
that's dealt with by a part of SPD-quantum gravity that's called charge mass dualism. And it's basically an extension of the very old theory of electromagnetic mass, the electromagnetic mass theory, which is where E equals mc square originally came from. It was discovered actually before Einstein, but with the wrong form factor. And so basically, the idea was that the mass of the electron is sourced from the energy that's kept in its force field. And when you do the calculations, then you find that exactly half of that mass of the electron can be explained in that way. And then somebody else found that if you account for movement, then you basically get the other half. So the whole mass of the electron can be explained in that way. And then the idea is to extend it to other forces. And I had this idea when I was thinking about neutrinos in 2017. I noticed that I think it was 2017, maybe earlier. I think 2017, yeah. Um, that neutrinos have a very small mass, and at the same time they are connected to the weak force. So I saw a correlation between having a small mass and having a weak coupling constant. And so when you do the analysis, you find that it doesn't predict masses as well as you would wish. Um, and that was the status for many years. But then in 2023, I accounted for the running of coupling more carefully, how the strength of a force changes when you go to um, different distance realms. And running of coupling is, of course, because you dive into the cloud of polarized vacuum, and that's why the charge and the mass and everything changes. So when you use the coupling constant that is effective at the at let's say when you look at the proton, you use the coupling constant that is effective there, or when you look at the quarks and the neutrinos. And so when you do that very carefully, you get very precise mass predictions. And the mass prediction I got for the neutrino is very precise. There, it's a 99 point something. Um, written the exact figure somewhere here, but yeah, it's very precise. Um,
So
and
what you're telling me is that on the one hand, using this idea of electromagnetic theory, you recover mass, but also you recover the inertial mass because half of it is
well,
mass.
mass is inertial mass. Like we speak about gravitational mass sometimes, but it's not really a mass. It's just a name that people call it, because in the mainstream, inertial mass and gravitational mass are the same thing, and so they don't care. They just call it mass. In my book, I also sometimes call it gravitational mass, but actually it's just particle count, and particle count is not mass. The word mass originally means inertial mass, and well, yeah, Newton thought it's the same as what is causing gravity, but yeah, the two should not be confused.
Okay, so let me make in fact, as I understand, Newton in his work had difficulty in explaining inertial mass. This was a huge, the point was Mach is the one who came with the idea of how inertia could be explained. And in this sense, he has a unified way of linking mass and inertial mass. Do I
I'm not
understand
sure,
correctly?
but this Machian mass idea that you're referring to, I know that it's called Machian mass, but I don't think Mach really came up with it. His idea was simply to explain why the bucket is bulging when it rotates. Um, yeah, about Machian mass, it really only works if you believe that in the equivalence principle, namely that inertial mass and gravitational mass is linked, are linked, because Mach said that that all the stars around in the universe create the reference frame and make cause a rotating water bucket to bulge. Um, and when you
Or
try to
equi-
explain mass in that way, you're saying that the remote star, the gravity from the remote star is defining the mass of an object. But gravity is not
no,
connected to
I don't
inertia,
think.
and so they two have nothing to do with each other. So you cannot use that way to explain mass, and it's even not a good theory because I mean it doesn't allow you to predict masses. The electromagnetic mass theory allows you to predict masses.
No, I understand this point, but I, my understanding is as follows: is that imagine this bucket with a thick wall, like a huge
Mm.
mass, and you increase the mass of this bucket. What is my understanding is that as you increase the mass of the thickness of the bucket, it will have influence in the dynamics of the water. That's my understanding. There's an influence of that. It's not that you can define mass of the water in regards to the stars or so on. It's more about the effects
But I
of it.
think that's the Machian mass theory. What it is saying that 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 the mass of an object is really defined by the distant stars.
There's an influence, basically, right? Because you cannot separate one and the other. There's the point that I understand from his work is that there's an invariance that
Mm.
you cannot break that invariance depending on which
Yeah, well,
formula.
I don't know how much we should discuss this because it's totally incompatible with my theory. It's relying on the equivalence principle, really.
Mhm.
But we could discuss the Machian principle in general, but the Machian mass theory is I don't think Mach came up with it, um, and it's an extension of it, and I don't support it. Well, but for mass principle in general, he was trying to find a way to define, uh, to explain why there seems to be a frame of reference, because a bucket of water that is rotating without touching anything, it still knows that it should bulge. Um, and so quantum mechanics is also telling us that there should be a preferred frame of reference because the wave function collapses everywhere simultaneously. And that's something that in Einstein's theory is not permitted to have to have to use the term simultaneity. It's because it's not defined in
Yeah.
Einstein's theory. But I think it's not so much. It's not very much ingrained in Einstein's theory. You could have. I mean, there was an alternative of Einstein's theory. Poincare's version of relativity theory was really it had an absolute space and absolute time, and um, you could not know which is the preferred frame of reference in which this absolute space and absolute time would apply. But Poincaré was using the term local time and proper time. So local time was the measured time, and proper time, nobody could know in what frame of reference that would be measured. So you could take the cosmic microwave background, and a lot of people think, oh, maybe the cosmic microwave background is this absolute frame of reference, or you could take the Milky Way, or you could. What I'm tending to do is I'm saying that the universe is being built since the emergence of starting from the emergence of life, and so we all have these entanglement connections with each other, and so for me, this is the absolute frame of reference is basically us here because my theory predicts that, or I believe actually that quantum mechanics predicts this, that we are alone in the universe. And
We are alone. You said
yeah,
alone?
alone in the universe because actually Max Tegmark has pointed that out too, that um, in quantum mechanics we really live in an island of entanglement. So we are all entangled. So we measure everything simultaneously, and we live in the same kind of now slice in space-time, if you were to believe in space-time. And and so then we
I
have
see.
an absolute frame of reference. And outside of that island of entanglement, there's basically just superposition. So when you see the sun, it's the image you see is 8 minutes and 20 seconds ago, and strictly speaking, it doesn't have a definite quantum state in the present. But of course, if you have a book lying on a table, even if you don't look at it, even if it's in superposition, in that superposition, the most likely state is still that it's sitting on that table and it didn't move. It could move theoretically if all the particles jiggle, but just by accident in one direction and it moves. But it's a very unlikely scenario. So things
Mhm.
have no problem of being unobserved and with their wave functions not collapse for a long period of time. You can leave your room for many hours, and if there's no observer in that room, it will be in a superposition, and that superposition can grow and become more and more superposition. But unless there are some very chaotic things happening in your room, like some gases or some very chaotic system. If nothing like that is going on, then your room will be just as you left it. Nothing extraordinary will happen. And
Okay.
some people say, because I'm saying that before the emergence of life on Earth, the universe was in all possible states at once and had all possible shapes. And then when life emerged, then one state was chosen, and then slowly through observation, the universe crystallizes out. Now, some people might find that that this sounds extreme, but the alternative is much more extreme. Like Hawking's view is that it's always like that, that you always have everything happen all at once and there's no collapse of the wave function. So
Yeah.
I'm saying that this kind of extreme scenario only was before life emerged on Earth. And you couldn't even say that time really existed back then because for time to exist, you need the wave function to collapse because something happening means there's a choice of state. If there's no collapse of the wave function, there's really no time. So it's more like mental help to, it's more like a tool to think of the time before the emergence of life as some superposition state because
I
that's what
see.
it effectively is.
Mhm.
I mean, the universe is 42 trillion years old, and that's a kind of like a virtual age. And in order to understand that age, you have to imagine the universe basically evolving in superposition for 42 trillion years.
Right.
Actually, more. It's actually 86 trillion years if you include
Oh my
the
God.
time before decoupling. So this is only the time after decoupling when the universe became transparent. The universe becomes transparent at a temperature of 2,900 Kelvin.
So what do you mean? In fact, I don't know about that. So what do you mean by transparent here? I don't, I have never heard of.
Before decoupling, that's actually also happening in the sun. Inside the sun, light cannot travel in a straight line. So for a photon to come from the center of the sun to go out to the surface of the sun, it can take 10,000 years or something, I heard. Yeah, so
Mm,
it's if there's if photons are not decoupled from matter, then they cannot travel in a straight line. That's why you cannot see beyond the cosmic event, sorry,
ah,
uh,
yeah,
cosmic
right.
microwave background. Actually, I misspoke there and called it an event horizon, but actually, I don't believe in true event horizons, like in general relativity. But this is pretty much like an event horizon. If you have coupling, then it's like you have an event. It's like you have an event horizon right there at the sun, at the
Ah, I
surface of the sun.
get it. I get it. So what you're saying is that this decoupling of photons from matter happened 42 or 43 trillion per your calculations.
42 trillion years ago, yeah, plus minus one.
So, and before that, everything was in superposition, and then it became somehow, I don't know.
Yeah, yeah, I didn't say that, but that's true. Yes, of course. If I mean, there's no way of observing anything, so it's highly superpositioned. Of course,
Hmm,
everything is superpositioned if you don't observe it. I mean, uh, your stomach is in more of a superposition than your hand, I guess, because you have more nerves on your hand and
hmm,
your arms, and inside your stomach there are less nerves, but still
right,
some, or your back and so on. So everything is superpositioned. Yeah.
right. And so your universe, your um, there, there's no, what is the notion of space and what is the notion of time? Then, or there isn't. I mean, it's all
Yeah,
superposition.
time, there's space and time is real. Like if you say that time is a dimension, then you're denying its existence because then nothing ever happened. If time is a dimension, then the past is still there and the future is already there.
Yeah,
And of course, the past is there in some sense, in the sense that the wave function is actually keeping a memory of everything that happened. So the wave function is actually identical with the non-local realm that is talked about in parapsychology, because you really every measurement is updating the wave function as part of the wave functions. As Heisenberg put it, the wave function is representing the knowledge of the collective of observers. He might
right,
have
right,
said just observer, but maybe he also said collective of observers. It has to be a collective, otherwise you run into problems like Wigner's friend, where you
yeah,
measured something and then I have to measure you for that to really be measured, and that
right.
goes up a chain, and then you you might need God to measure all of us or something. So
Right.
that doesn't make sense. If you measure something, everyone has measured it.
Mm. Okay, so let me get this. So what is the notion of space? There is no, in your theory, the notion of space is not as what we think in
Well,
relativity
the space is
theory or
granular. You have space quantum,
space
which is
quantum.
pretty standard to quantize space in quantum gravity theories. But the
Right.
difference is that all other people are using the Planck length as a
Yeah,
standard pixel size, and I don't have that. I have variable sizes and much bigger in general. Like a resting electron would be have the size of 10 to the power of minus 21 meters.
okay, right. I see. Mhm. So it's variable with regards to the particle that you observe. Do I understand correctly?
Yeah,
The
it
mass.
depends on the mass energy, and it's basically like a scaled up version of a black hole. So you see, I don't have classical black holes. Like a black hole is proportional to energy, and in my theory, gravity doesn't depend on energy but on baryon count. So
Yeah,
the black holes in my theory are different from GR black holes, but my elementary particles are quite similar to GR black holes, but just much, much bigger. It's like if you scale up the gravitational constant to the strength of electromagnetism, that's how much it's scaled up,
ah,
or like the
right.
strength of the quantum forces. Yeah.
Okay. So I get, I now understand your space, the quantum space. and the concept of time is tied to the observer, correct? Do I understand?
Yeah, I mean, the concept of time is basically just the normal concept of time that we have in everyday life, that the things change and are not static, whereas in Einstein's theory, they are static. And Einstein didn't even like this idea at the beginning. It was Minkowski who came up with that, and he was not too happy with it at the beginning.
I get it. Okay, okay, okay.
And it's also unacceptable in quantum mechanics because quantum mechanics is basically the main rule of quantum mechanics is we exist in all worlds that are currently indistinguishable, temporarily indistinguishable. And this definition relies on time being real and things to change.
Yeah, but as you say, the future does not yet exist.
Yeah.
It's right. It's
Yeah, and that's what quantum mechanics actually requires, that the future does not yet exist.
yeah,
Because the
right.
future is not predetermined. Quantum mechanics is non-deterministic. So if you have a fixed future, then that it doesn't work. Then it's not
Right.
then your probabilities wouldn't be probabilities anymore.
Yeah, I see. Okay. And so then tying into so then in this framework, the how do you see the concept of light traveling in your space? Do you still believe in say that there is a light speed is constant
Yeah, so
and
so
so how
Einstein was actually using a variable speed of light in general relativity until he published until he finished his theory, or shortly before, I don't know. He was always saying that when you go lower in the gravitational field, the speed of light is lower, and that's why time seems to pass slower. So actually, to say that the speed of light is lower and to say that the time passes slower is equivalent. They're indistinguishable, and the equivalence doesn't end there. You can change any of the fundamental constants, C, H, or G, with G not really being fundamental, but it doesn't matter if you use you can just switch to Gy, the chromogravity constant. So if you change any of those three numbers, basically you cannot notice it. You will not notice it. But if this change is only in a certain region, then this is basically translate to time dilation. It's like a Lorentz transform.
Mhm, mhm.
So maybe I should explain how SPD-quantum gravity explains speed-dependent time dilation
Yeah.
and gravitational time dilation. So speed-dependent time dilation, you're basically saying, okay, you have a spacecraft and all the atoms of the spacecraft have more energy than before the spaceship started on its journey. Um, and that means that because the size of those space quanta depend on energy, therefore they are inflated. So, but if you increase the size of elementary spaces homogeneously in one frame of reference, like in your spaceship, then you cannot really notice it. It will only manifest in the discrepancy between different frames of reference. So that will also be time dilation. So increasing I mean, you can increase the size of elementary space, but because c, the speed of light, is also part of the formula for their size. You change that, you change the size of elementary spaces. So that's speed-dependent time dilation, and gravitational time dilation is like this. The reason gravity is so weak is because there's already this huge sea of virtual particles in the quantum vacuum. And so when you add a single hypercharge that emits gauge bosons, you increase the density slightly, but it's like a drop in the ocean. That's why gravity is so weak. While on Earth, you don't only have the background, the quantum vacuum background, but also the background that comes from the gravitational field of Earth. So you have two backgrounds stacked on top of each other. So then your gravity is much weaker. So the gravity between two objects inside the gravitational field of Earth, as measured in a Cavendish experiment, for example, is weaker on Earth than in space. but again, it's like a uniform change of constants, and you cannot notice it, you cannot measure it, but it manifests in a discrepancy between frames of reference. And
Okay.
so that is, again, time dilation.
Okay, I see. I see.
I came up with that in 2018. No, I think 17, and then the speed dependent time dilation in 2018. So the easier one I did later. Um, and before that, my only hint and how to derive special relativity and time dilation in general relativity was this hint that exists in twistor theory, which Penrose uses. Basically, is using the projective properties of twistor space to say, okay, somehow special relativity is going to come out of it. But I dismissed this kind of hand wavy explanation. Well, it's not like it's not so bad, but it's not needed anymore in SPD, and it never really quite fit. I was thinking a lot about the projective properties of Riemann spheres and twistors in the early days because SPD was born out of trying to understand twistor theory, and by doing so, reading. I was reading a book about it that had 3 chapters on twistor theory, and I was reading it like maybe 10 times, 20 times to kind of understand. And then at the end, I just made up my own twistor theory. Yeah, like he
Okay,
was using spin directions, and he said, okay, if you have only one particle, then directions don't exist. But if you add enough spin directions together, then you get a three-dimensional space. And but for me, I don't know how you can get a space just out of lines, basically. So I thought, okay, when you have spheres, then they can overlap, and you can, if you move on the surface of the spheres, then you can actually move
right. Yeah, right, right. I see. That's very interesting. So your whole space is full of spheres, basically,
overlapping ones. Yeah.
overlapping. And what about the in between the spheres? What is that? Is it
Yeah, it doesn't exist. That doesn't exist. There's nothing in between. The only space is so space is actually two-dimensional, and you only get a feeling for three-dimensionality by adding all these spheres. And if you were like using one-dimensional elementary spaces that which were like circles, and you add them all up, then if you can access 10 directions, you already get a feel of 2D. But for 3D, I think you would have like about at least 100 for that to be a feeling of three-dimensionality. So that's why in my formula for granular dimensionality, I have divided by the square root of n instead of just divided by n. So if it was 2D, then n would be enough. So 10 directions would already get you close to, it would go to 1.9D dimensions. But here you would need at least 100 or more to
so are you
for it
referring
to feel kind of like 3D.
are you sorry, I think I'm missing this point. Are you referring to fractal dimension here? The space
Um,
or not?
I guess it's a similar concept, but I'm not using the fractal dimensionality that is out there. I'm calculating it in a different way.
Hmm.
It's using the number of connections from one elementary space to other elementary spaces. And I think fractional dimensionality and fractal dimensionality, I didn't look much into it. I think it works quite differently. I looked into it briefly, and it's quite different from what I have.
Because your dimensions are not integer, they're real numbers, if I understand correctly.
No, they're yeah, they're real numbers. They're not integer. Yeah. Mhm.
And that
Yeah, it's
sounds
two point. So the dimensionality of space is basically 2.99999, and there are 35 nines there, and then so that's why electromagnetism is 10 to the power of 36 times weaker than gravity. That's why gravity is so weak, because there are already so many connections there.
let me go back to this connection. So I'm missing something. Okay, imagine two dimensions. You have um, um, Because I don't see how.
Like a flower of life, but just with variable size for the. So you think you're traveling in a straight line, but when you zoom in, you see that it's actually zigzagging. So if you had more elementary spaces here, then it would curve and it would bend. So that's gravity. So I'm not completely abandoning the idea of geodesics. I'm still using it, but I would say that my theory has a more straightforward concept of geodesics than Einstein's theory. Because in Einstein's theory, the geodesics are just straightest path in not in space, but in space time. So so time is not a dimension. So that for me, Einstein's theory doesn't really have geodesics. And at the end, how much it curves still depends on how fast the particle is moving, and if it moves faster, it won't bend so much. So yeah, it's geodesics. Even Einstein's theory is not so straightforward. But the
Uh,
general concept is there that basically particles move in straightest line. It's just not straightest line in curved space, but instead in granular space. Basically zigzagging. If I throw down this, it falls down because there are more elementary spaces down there, and that's why when it goes zigzag like that, there are more zigs than zags. If that was zag and that was zig, then there are more zigs than zags, and that's why it falls down.
right. Okay, but in your granular space, again, I want to go back to this point where in between the granular, you have void. Is that the quantum
No, that void doesn't exist.
does not exist?
It doesn't exist in the same sense that like when you have a closed universe in Einstein's theory, a closed universe, then okay, you can imagine that there's some higher dimensional space outside of it, and you would call it hyperspace. In Star Trek, it's called subspace. I don't know why. And but you have no reason of assuming that. And aside from Kip Thorne, who likes to draw it in his diagrams and label it as hyperspace because it
Yeah.
sounds
So
cool,
what I wanted to
it doesn't. It's not really generally assumed to exist.
yeah, okay, I can understand it doesn't exist in the physical notion, but could that be the quantum vacuum part?
No, the quantum vacuum is the elementary spaces. That's the quantum vacuum. But I mean,
Ah,
it's so totally full. I mean, they're everywhere. These bubbles are everywhere. So it's so dense that, I mean, inside your bubbles, you have other bubbles. It's all full of bubbles. It's like a
okay.
bubble tea.
Oh, okay, right. Okay, it's a bubble. That's the quantum vacuum, and then the particles emerge from these quantum bubbles. Do I understand correctly? Like the
Well,
observable.
the real particles are also bubbles, but they're real in a sense that they don't just disappear very quickly.
Okay, what distinguish one from the other then? It's just the
That
time that.
the ones are real particles, the other ones are virtual particles. So if you ask that question, it's basically asking what are virtual particles. My interpretation of what virtual particles are is that they are basically particles that are in a superposition of existing and not existing.
Ah, okay, I
So
see.
they are not
Okay,
in every of the indistinguishable worlds.
okay, okay, okay. I get it. I get it. I
And they
think I
have to
see.
disappear before you can measure them. That's why they can only, the time they exist is determined by the time energy uncertainty equation.
Okay,
E
okay. I
times
see.
t equals h bar divided by 2.
Yeah, right, 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 right. Okay. Okay, I think I begin to see.
Mm.
I think I begin to see the picture of what you're trying to say. Mhm.
Yeah,
Uh,
and do you like me to talk about what I discovered yesterday? Or you want to
before
continue with your questions?
yeah, I just want to finish before
Yeah.
one question. So,
And I don't know how much time we have left. Maybe you can only do this question.
yes, I don't
Do you
know.
see the time here? I don't see it.
I don't see the time either.
Mm,
Uh, yeah. Anyway, so let's
mm,
okay. So, in Einstein's theory, again, going back to your zigzag analogy, in Einstein's theory, it has to do with the mass bending space and then creating the, so for
So energy
geodesic,
bending space, more
yeah. And
precisely.
in your case, is this
Baryon
uh,
count.
Arian count, right?
And it's not
Okay,
bending,
okay.
it's just increasing the density of granular space. More bubbles, basically.
Ah, okay, okay, I get it. Okay, okay, okay. Mm, okay, I'm taking notes because I don't want to forget it.
Yeah, sure.
Mm, it's fascinating.
Mm,
Okay, okay, I get
thank
it. So
you.
I think I'm satisfied with some of the questions that I raised, and now I think this will better guide me into reading your book. In fact, so that would be really very
Yeah,
a
so
great.
yeah, so
Yeah,
SPD quantum gravity consists of the similar worlds interpretation. So the similar worlds interpretation is basically saying that we exist in all worlds that are currently indistinguishable to us at the moment, and so that solves the entanglement interpretation problem, like the spooky action at the distance problem. Basically, if spins are orthogonal in each of the classical worlds that we exist in simultaneously, then it's not strange to measure and choose one and to find that they're orthogonal. So then it doesn't need to be any superluminal communication. It's only mysterious if you say this one is fuzzy and this one is fuzzy and they don't have certain spin directions, but when you measure, they all both have the same. So there's nothing strange about it at all. It's very straightforward.
explain. Oh, explain. That's crazy. Can you explain? Explain again. Sorry, that's
Yeah.
very
So
non-trivial. Non-trivial.
yeah. So we exist in all worlds that are indistinguishable to us, and each of those worlds. If you imagine each slice here is one world, and the spins are orthogonal on each one of those worlds, spin up and down, then and in that world is like that, and that world like that, and that world like that. So if you measure it and find them to be orthogonal, it's not strange at all. It's only strange when you see this one is fuzzy and this one is fuzzy, and they're kind of, if you say the particles are in superposition, then you get in trouble. But if you say the world is in superposition, then everything is fine.
Ah, okay.
If you say the particles are in many places at once, then you get in trouble. But if you say we are in many worlds at once, then you don't get in trouble. It solves the Einstein-Rose-Podolsky paradox.
Yes, I see.
And I mean, in the mainstream now, the only solution they have is basically to say that there are tiny wormholes between the particles, and that's how they communicate, like with the walkie-talkie. Like, hey, I've been measured this. Make sure to be measured the opposite. Mm.
But so you do believe in the many world interpretation of quantum mechanics,
No,
essentially.
no, no, definitely not. Only the worlds that are indistinguishable. And so we all look exactly like this now. Only difference is that maybe some particle in your nose or some tiny bit in your skin is not in this position but in that position. Like anything that you cannot see right now, that is in superposition. Or you have a particle, it flies like this and like that simultaneously because of a beam splitter. And so the reason it flies this way and that way simultaneously is because it hasn't landed in your eye. Also, it didn't hit a detector. If it hits a detector and it lights, so this light is blue and this light is red, for example, you can distinguish that then the wave function collapses and you have one outcome. So it's not like the many world interpretation, very different. It's a similar worlds interpretation, similar worlds.
I don't see yet the difference. So wait a minute,
And the
because you
difference is you would be sitting here and at the same time being outside. Every version of you, you're a good person, right? And at the same time, in the other worlds, you might have killed all of humanity. That's the many worlds interpretation, and that doesn't happen in my interpretation. My interpretation, only only the worlds that are indistinguishable are real. They all look exactly the same. And actually, the
But
number of worlds is entropy. Then the logarithm of the number of indistinguishable worlds is the entropy of the world.
so all these worlds are in superposition.
Yeah,
All these
they
possibilities.
are parts of the superposition of the universe. Yeah.
And so what you're saying is that if I measure one of those worlds, like
Then all the
entanglement,
others go away, don't exist anymore. Yeah.
right? I
You have
see.
a new equivalence group. It's called an equivalence group
Mm.
in similar worlds interpretation.
Would that explain entanglement?
Yeah, yeah,
I don't.
right. Exactly. Yeah.
How does it explain it? I don't see yet how, because in entanglement you can actually put one particle in the moon and spin, you know, change the
Yeah, and
spin of
that's
this.
not strange. That's not strange because of spin momentum preservation, they have to be orthogonal. Otherwise, it's not the sum is not zero. So in each of those worlds, they are orthogonal. So it's not strange that when you measure, you find them to be orthogonal. Nothing strange happened. It can be on the moon, fine, but if you measure them to be like that here on the moon and here on Earth, it means that in that particular world they have always been like that.
Yeah, no, so I understand this, but then what you can do then is um change the spin of this guy, and this guy will change the spin, as you say, conserving momentum. But the speed at which it happens, it's a non-local phenomenon, right? That's why people can't explain this.
Not really. The only reason it appears to be, of course, it's non-local in the sense that the whole world is updated, is in those similar worlds are updated simultaneously. So that is faster than the speed of light, the update. But nothing is really traveling. I mean, the only reason it appears to be faster than the speed of light is because we are all the indistinguishable worlds at once. Nothing weird is happening actually.
Okay, so what you're saying, this, okay, it's quite hard to wrap around, um, because of
Yeah, most
this.
people like this property of the similar worlds interpretation very much. It's what people most relate to in my theory, at least in the early days where I didn't have so much that people uh, lose track. But yeah, in the early days, this was the most popular part of my theory.
Right, yes, right, right,
And
right.
the solution seems to be kind of too simple. And it is too simple actually because you are in all the worlds at once, and but that way you can only explain like a probability mountain, not a probability wave. Probability is a wave like, and for that you need space particle dualism. You need the particles basically to get out of our universe and get in back again. So it's a surface, complex number surface with the surface area z, where z is a complex number that goes around the origin of the complex plane. And that way the real component shrinks and grows again. So it's like an oscillating complex mass. And that's why the probability to measure a particle on a certain trajectory always goes up and down like a wave, instead of just being a mountain. Like when you only use similar worlds interpretation, which is very simple, you only get a mountain. So here the probability is highest and then it goes down here. It's not a wave. Yeah.
Oh,
So you need to combine the two theories in order to explain why probabilities are wave-like and not just simple mountains.
right. But when you do experiments on entanglement, you are okay. Because you're going from one thing to so on the one hand, you start with this similar worlds interpretation that you have all these
Mm,
worlds stacked up and
mm,
superimposed. But when I do experiments, I do experiments on one particular world. That is, I measure,
mm.
but then I can change the spins on that particular world that I'm.
Yeah, you're always in a different collection of worlds.
Yeah. So once I select a world,
Mm,
and then I can run experiments, and still the entanglement property is
mm.
crazy, even though I selected one of those worlds.
Yeah, I mean, without having this group of worlds, I mean, the history, your past, our past is not even the past in any of the similar worlds. Everything that's happening around is always a combination of the many worlds. That's why you also cannot have space-time. If you imagine there's space-time in every of those worlds, imagine every world is a space-time. It doesn't
Yeah.
work because the quantum forces are emerging from the collection of similar worlds. So a single world will not have a space-time. I mean, you could imagine space-time, but then it would be space-time of a world that doesn't, where nothing is happening because there are no forces. Even the fact that there are forces is a result of us being in these similar worlds.
Mm-hmm. 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 Okay. I need to read. I need to read. I must admit that's quite tricky, but I
Yeah,
must admit.
that's chapter 1.1, 1.2.
Oh my God! If it starts with chapter one, that complex is a it's gonna be
Well,
so
basically,
so.
I'm asking people to abandon the notion of space-time already in chapter 1, yeah.
Yeah, precisely.
Mm.
So
But
there
I
is no
mean,
space.
quantum mechanics asks us to reject space-time basically because, as you can read in many books, quantum mechanics doesn't have space-time. It's really uh, one space at one time, and it's absolute in quantum mechanics.
Um, as I understand it, from a maths, you have a Hilbert space, but Hilbert space is an
Mm.
abstract. Point is that there is a quantum process that is happening, and you cannot
Yeah, but
observe
every
it.
point in Hilbert space is basically just one moment. You don't have a space-time there. You have space-time in Einstein's theory and Hilbert space. They're separate. Mm.
I completely agree. I completely
Mm.
agree. So the Hilbert space is an abstract space, has nothing
Yeah,
to
and
do with.
I don't really believe that we live in a Hilbert space because in quantum mechanics, every component of Hilbert space is still there's still superpositions. The components are not really classical worlds.
Correct. Correct.
So my world is more like phase space. Phase space, you have every position and every point in phase space is one configuration of the universe. And so for every particle, you have 3 dimensions of space and three dimensions of impulse. And so that's phase space. And uh, my idea for the similar worlds interpretation came actually from thinking about how Penrose described the passage of time as a point in phase space moving along and going around in phase space. That's how time passes. But then I thought, but wait a moment, there are no definite particle positions in quantum mechanics. So how can this be? So then I extended this point to a cloud. So you have a cloud that moves around in phase space, and the cloud grows every time we don't measure. And every time we measure, it collapses again a little bit. Not totally, but a little bit. And so you have a oscillating cloud of consciousness in phase space.
So this phase space, can you repeat again? What is the dimension? So what are the so 3 dimension of space and the
Yeah,
other
six times n, 6 times n, the number of particles.
velocity and
Yeah, but I
space.
don't I don't take it I don't take the area outside of this cloud seriously. I mean, I mean, even in Copenhagen interpretation, you could imagine that all these different worlds where you are not sitting here, but you went on holiday or something. You could imagine that all that is still existing out there, but it doesn't help to assume that. For me, I just assume that this cloud is real, and the phase space is just the mental help. It's just a tool. It's just a diagram. You can draw diagrams, but doesn't mean you live in a diagram.
No, no, I agree. I agree with this point, but I just want to understand your diagram to then for
Mm.
me to so your phase space normally is velocity, no, and position, right?
Impulse, impulse and position. Yeah.
Right. And so what you're saying is that you have a cloud of
Mm.
superposition of many worlds, right?
Yeah.
And as we measure, we observe as we measure, it collapses, and then
Mm.
it oscillates as we measure, as observers measures. That's
Yeah.
what you say.
Yeah. Yeah.
And this cloud is form of these
Yeah, and you can, Penrose does it often in his books. He shows phase space and shows compartments in phase space which are similar to each other. And
Mm.
so that's the entropy that's talking about entropy.
Okay, okay, okay. And this cloud is not space-time, to be clear, right?
No,
So
it's just one moment. It's just the present, just the now. Yeah.
right, I see. Okay, okay. I think I get the intuition of
Mm.
your theory. I'm gonna read the book. I really need to to read it.
Has it
But it's
arrived yet?
huh? No,
Has it?
it's no, no, not yet, not yet. It's I got it through Amazon, and so eventually maybe it will arrive this week or next week. But eventually I'll start reading.
Mm.
But yeah, I do appreciate all your explanation. And if I have doubts, I'll come back to you with questions.
Sure.
Um,
Okay.
yeah. So I just have a last question, which is, how are you promoting this work? How are you trying to make other researchers like experts to know this work beyond just
I just upload papers on ResearchGate and academia.edu, but now I'm focusing on ResearchGate more. Well, and I make videos, interviews with you and Sheldrick, and I do experiments and I upload them. Yeah, that's how I promote. But I don't go into forums and stuff. It's too much takes too much time. I don't even do on Facebook. I make posts on Facebook, and it helps a lot to think. Like the idea from yesterday. Yeah, I, I post stuff on Facebook, and sometimes I have the thought half finished, and then I just start to write, and then I pause, and then maybe, and very often I get the rest of it while posting, and I think it's much easier to think that way. Or of course you can go on a walk, which is it's a good place here to have a walk. It's near the forest.
okay,
Yeah,
great.
so I do that when there's a big problem. When there's a smaller problem, it's sometimes enough to just think while typing on Facebook.
So
So
but
Facebook has a very good record of what I'm doing. Yeah.
and are scientists, or what I mean is that um don't you want to give talks to scientists like in conferences and things like that?
Yeah, but yeah, you can send me something if you see a good conference. I mean, I was not in Europe for I'm only sometimes in Europe. Now I will be here longer. Um, Yeah, and I mean there are a lot of conferences which I was in some conferences in 2019 in Japan and in Italy, and yeah, a lot of them are just scams because you have a bunch of people there talking. The organizers don't have any particular background, and most of the speakers are just talking to hear themselves. There's no discussion or anything,
That's
and
true.
yeah, and they're not necessarily famous. And yeah, I mean, why should you pay money to talk? I mean, you should be paid money to talk, not the other way around.
But
And
there
and
are
if there's not even yeah, it depends what the conference is. If it's a good conference, if there are some famous people there, then yeah, sure.
yeah, no, that's what I meant. Like where you go, like
But
there
I
are
don't have a
scientists.
secretary or something who could look, okay, go to this conference, go to that conference. Because what I'm doing is I'm doing research. I'm not doing stuff just for promoting myself or something. Okay, making a video is while making a video, I'm still doing the research. But if I look at conferences, I'm yeah, I should probably do that. Yes, but
Yeah,
I
that would
haven't done that much.
yeah, because I think it would be interesting for you to make your work known to the larger scientific community. Okay, the book
Yeah,
is a
but how do
starting.
you find the very good conferences? I mean, how do you distinguish them?
Well, I mean, you are citing the right scientists, and those scientists are attending those conferences.
Okay, just look for the people who are attending the conferences.
Yeah.
Yeah, like
So that,
only one I like. There are a few people I like to meet. Like there's Roger Penrose, of course. Yeah, yeah. I'm meeting with Wannes Kafatos sometimes. He's a famous Greek physicist. Um, yeah, he invited me to meet him in Greece. Yeah.
and is he working on your on? Is he? I mean, the fact that he
No, he's
invited you.
mainly doing promoting or talking about the spiritual aspects of quantum mechanics.
Okay.
Um, yeah.
Okay.
There's Fischbach in America, but yeah, he basically retired a year ago. He had a stroke, and I
Mm.
called him, but yeah, he has memory loss, and
Oh, God.
yeah,
Okay.
he's always very excited to talk to me on the phone when I reach him, but yeah, I don't think he remembers much. Yeah,
Mhm. Yeah. Right. That's sad.
yeah.
Um.
But
But
I'm
what about?
connected a bit to the his students, his former students. Yeah.
Oh yeah. That's.
So
Couldn't
do you
they?
know who is Fischbach? Ephraim
I,
Fischbach.
no, I've heard of this name, but I don't
Yeah, he
know.
is the one who discovered that the Atwood experiment from 1922 is actually disproving the equivalence principle. The diagram that I showed you last time, where they were comparing two different chemical compositions on a beam on the Atwood balance, and actually all of them were different. The only reason that Atwood and Einstein thought it proves the equivalence principle is only because the differences were extremely tiny.
Okay.
But they were actually not disagree. They were actually disagreeing with the equivalence principle.
That's.
The standard deviations were not overlapping. And he
Oh, really?
discovered that the pattern follows exactly um, the binding energy. So Fishbach basically wrote down an equation that I have as well. The only difference is that he has a coupling constant, making the effect incredibly small, smaller by a factor of 100,000.
Oh, wow.
Normal books on gravity actually mention his work in the 90s, but nowadays the new version already didn't. So here they mentioned the adverse balance, and so the theory of Fischbach was in 1986, and it's mentioned. Yeah, it's mentioned at the beginning of this book. They discuss it here. Um,
What? Can you show me the book?
Yeah,
The,
it's
the,
mentioned in many books. Actually, in the 90s, there was the whole frenzy of trying to measure such effects, but they actually, because the adverse balance is constructed in a way that makes these effects incredibly small, so small that it's almost impossible to measure. And that makes people think that any such composition dependent effects must be extremely small and not big like the effects that I'm talking about. Um, and he was framing it as a fifth force correlated to the strong force and gravity somehow with a reach of only 20 meters or 40 meters. It depends on the version, it's an arbitrary number. And yeah, it's very different from my theory, but the formula, the basic formula, is the same, just he's making it very small by using a coupling constant.
so what is the name of the authors? I can actually, I may have to read it as well.
Um,
Hans, okay, yeah, Remo Ruffini. Okay, right, right, right.
Yeah, but it was in all in many books in the 90s because they all tried to measure it. The experimenters tried to measure it, but then they didn't really try to measure it because they were just looking at violations of the inverse square law because they were focusing on his claim that it's a short range force.
Right.
And he was actually the one who made the term fifth force popular. So if you often hear the term fifth force, that's because of him.
Okay, I see. I see.
There's also an
Okay.
endorsement from him in my book.
Oh, nice.
Yeah,
That's super.
yeah. What did he
I mean,
say?
I will see. I mean, I what about in China? You said you have sponsors in China. Maybe they could find.
No. I don't have sponsors in China. That's long ago. There was one sponsor in China 2020 until 2022. Yeah, but he was more interested in my etymology research.
Oh, okay. I see. I
Yeah,
see.
he said, Ephraim said, Fishbach said, Sky Darmos has done the community a great service by tabulating the results of a large number of experiments, referring to my meta-analysis of Big G.
That's super cool.
Mm,
That's amazing, to be honest.
mm.
Um,
Many
I'm just
physics
wondering.
students actually know about his know about him. Many physics students know about him.
Yeah, right. And so through his students, couldn't you get in touch with the community, uh, you know, of scientists
Well, I'm
interested
in
in.
touch with many people, but yeah, I don't know. I don't know what the goal is. What you're trying to say.
Well, what I'm trying to say is that you to run this to continue your research, you need to be sponsored in the
Well,
future.
I
If
am
you
sponsored. I have two sponsors. Didn't you know that?
but for how long? The question is in academia
Indefinitely.
okay. In that case is okay. In that case, it's safe because I thought because in academia maybe you could find fellowships and labs that could help you, for instance.
My current sponsor can sponsor any device, any experiment. It's just that I could buy a gravimeter. He could sponsor that, but then what? I mean, I would have to open it and swap out the test mass. And what if I destroy it? It's like 10,000 euros. So maybe it's better to try and build something myself.
Yeah,
Um, yeah, using lasers, maybe attach lasers to some mechanical scale. Basically, I have to measure force with very high precision. Um, yeah, I've tried to find. Yeah, most of the force sensors they're actually not measuring force; they're measuring mass. Because if you have a robot, you build it into a robot. You're not interested in having it feel different forces when it's down here or up there in a 10th floor or something. So that's why for the value, the readout to be very stable, they just use this force restoration mechanism, which prevents you from measuring gravity.
but that's what labs in academia could help you build, for instance.
I would not approach labs. I would approach companies that sell scales. But then the problem there is they might want me they might require that I produce like 10,000 of them or something.
Yeah, exactly. But that's why labs exist in academia.
Yeah, sure. Sure, if you know good lab, yeah. But I'm busy doing research most of the time, so I don't do this kind of organizational work. Not too much, a little bit, yeah.
Okay.
I
Okay.
try to reach different people. I went to a company in Swiss that they were selling a force sensor for 20,000 euro, and it turned out to still have a force restoration mechanism built in. They were not clear about that. I went there and tested it, and yeah. Basically, if it doesn't have that, then it's gonna fluctuate, and people, I guess, people don't like that.
Yeah.
They'll like it to fluctuate. And another time, somebody sold me a load a load cell, and he said that it could measure very precisely, but actually it wasn't. I mean, I had read the data and couldn't, but he guaranteed it, and I tried it. It didn't work. It was fluctuating all over the place. Yeah,
I'll
it's
see. I'll see
difficult
if
to
I,
build these things.
I'll see if I can find labs that could help you do this
Thank you.
experiment. But for that, I need a few things. So normally labs they are short on money, for instance, but they so can your sponsors help fund aspects of it and they help you
Yeah, sure,
build
of course, yeah,
so that they have the funds to do this to help
yeah.
you. Okay. So then let me see if I can find. labs. I can't promise anything because I don't know. The labs that I work with is mostly in neuroscience. But maybe by asking around, I could try to see if there are labs who could help you with that. And it's quite rare. You're actually quite lucky to have indefinite sponsor because in academia, we always
Well, it's not
competing,
academia. It's not academia. So
but it's not industry either.
it's
So
industry. Like
you are within.
the one is real estate, the other one is like yeah, like financial or something. Yeah.
Okay, okay. Well, okay, that's different. But how can they be interested in gravity? Like real estate is how can real estate be interested in
The
gravity?
one in Swiss, that's my cousin. She married a billionaire.
Okay, okay, okay. Fair enough.
Yeah.
Okay, fair enough. Yes. Okay. In that case,
But
let
that's
me
actually
see.
the smaller one. The bigger one is in the US.
Okay,
Mm.
in the US. Okay.
OSS Capital. Yeah.
Yes.
There are a lot of people who tech. So he's some um, tech expert, crypto, everything.
Right.
I guess a
Right.
bit like a Elon Musk kind of guy,
Wow.
but not
Yeah.
as big.
No,
But
that's
still
great.
quite big. I mean, his company is not so small, I think. Yeah,
Yeah. So, but that's great.
and
That's really.
he has plenty of videos online. Yeah, you can check him out. Yeah.
What's his name again?
You just look for Joseph Jacks.
Joseph Jacks. So
Mm,
yeah, that will help me to contact labs and say,
mm.
look, Sky has funds and he wants to
Well,
collaborate. And
of course, I have to ask in every case, and so, but yeah,
oh, of course,
most
of course,
likely.
of course, of course, of course.
Mm.
Joseph, just Joseph Sachs, right? Did I understand correctly?
I sent you the name later.
Okay. And then I'll contact these labs and then see if they, and then I'll let you know once I identify one for you.
Yeah.
Yeah. Okay, great. So thanks a lot for your time.
Mm,
I will definitely, I'm looking forward to read your book. It's gonna be
mm.
a I don't know, a different world, basic
Yeah.
different world.
Thank you.
It's very interesting. Thank you so much.
Hmm.
So
Okay.
can
Thank
you
you.
send me your video
Mm.
once you download it?
Yeah. Okay. So should I click stop recording or just exit the chat for it to be
Yeah,
saved?
I think you can stop recording and then once you exit, it will save it. I think. Look at it.
Pause and then